Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Sophia Chen. Ice is a staple of both everyday life and laboratory science, from the cubes of it in your freezer, to the crystals of it in the atmosphere, to the cryopreserved organs used for medical transplants.
So it has always been really of particular interest for physicists and physical chemists to studying how this phase transformation occurs, how water crystallizes into ice, and also how ice melts into water.
That's Jingshan Du, a materials science researcher at Pacific Northwest National Laboratory. His team wanted to understand how ice forms with high resolution, so they imaged how ice crystallizes by using a transmission electron microscope.
What we really wanted to see is how ice crystallizes on the molecular level and what's the consequence of such crystallization.
To do this, they dropped a tiny droplet of water on a grid made of copper that was covered with amorphous carbon membranes. They used the amorphous carbon because it is extremely smooth, fairly hydrophobic, and not too flexible, which allows a single ice crystal to form when they cool it with liquid nitrogen.
Then we put another TM grid on top of the droplet and then press it down to make a sandwich. So that gives us a very thin liquid water, thin film trapped between carbon membranes.
The thin films of ice ranged from about 10 nanometers to 100 nanometers in thickness. Using the transmission electron microscope, they fired a beam of electrons through the ice, which got scattered and diffracted by the ice crystal. The diffracted electrons formed an image that indicated how atoms are arranged in the crystal, and they captured this image using a camera. They were able to capture images with resolution under 2 angstroms. Imaging ice this way had been difficult because the electron beam tended to damage the crystal.
Whenever we shoot electron beam or other type of radiation sources, they will perturb and damage the crystal so much that it's really difficult to zoom in and see the atomic level structures and the dynamics.
Du's team was able to achieve this in part because they cooled the sample cryogenically with liquid nitrogen, which reduced the damage caused by the electron beam.
Usually a lot of the chemical reactions and physical processes will be dramatically slowed down compared to room temperature.
The carbon membrane sandwiching the ice also made it possible to use the electron beam without damaging the crystal. The carbon membranes protected the ice from sublimation in the high vacuum. It was also a good electrical conductor, which helped reduce charge buildup on the ice. Charge buildup can cause additional damage to the crystal. From the images they took, they studied how defects such as skewed crystal structure affected the ice.
When we actually zoom in and have the required spatial resolution, we saw that there are a lot of subdomains that are not necessarily aligned perfectly to the zone axis. They are actually slightly tilted from each other. And the ice is actually okay with that.
Even when the crystal is tilted around 1 degree from the norm, the ice did not have much internal strain. The ice crystal structure was similarly stable when it contained a gas bubble, too.
We were really surprised how ice is so flexible that it can tolerate a lot of structural defects. Basically, the take-home is ice doesn't really care about how much tilt you have between subdomains. The energy will be pretty similar.
Du says these imaging studies can help researchers create ice in a more controlled way. This could help researchers working in cryopreservation, for example, to prevent crystal formation, which can damage the biological tissues being preserved. This work was published in a recent issue of Nature Communications. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X @MRSBulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.